Today we're talking about spontaneity of reactions. And when we use the word spontaneous or spontaneity, we typically think of it in sort of like human personality terms. Someone's spontaneous if they do things without a lot of planning. In a reaction, spontaneity means something a little different. It basically means it's something that happens, I want to say on its own, because a lot of spontaneous reactions do need a spark to get going. But a spontaneous reaction is one that occurs without continuous outside help. So if you're baking a cake, the reactions that are happening are not spontaneous, or at least, some of them, like the breaking down of baking soda to give you carbon dioxide to make the cake rise. Because if you stop adding that heat, that reaction stops. Whereas if you, strike a match, yes, it requires a little bit of help to get going, but, it then continues on its own. It just needs a little bit of a push to get going, and then the reaction occurs on its own. So it's still considered a spontaneous reaction because you don't have continuous outside help. Rust forming would be another one. If you leave a piece of iron outside, comes into contact with water, comes into contact with oxygen, you're going to get iron 3 oxide. That is spontaneous. Now, it is important that you understand that spontaneous reactions don't necessarily happen quickly. And I think rust formation is a great example of that because, it could take years for, just a couple grams of rust to form on a piece of iron, happening very, very sort of slowly and gradually, but it's still spontaneous because it didn't require a big input of help. Okay, so there are two things that determine whether or not a reaction will be spontaneous. It turns out that most spontaneous reactions are exothermic, so they give off enthalpy, negative delta H. And so the most common reactions that we think about, combustion, synthesis, double replacement, single replacement, most of them are spontaneous or in part because they give off heat content. They lose enthalpy. They have negative delta H's. But there's another factor, and this one we haven't talked about yet. Most spontaneous reactions result in an increase in entropy of the system. And now entropy is a new word for us. It basically means the randomness or disorder of a system. And not everybody likes that definition. You might have a teacher in the future that says, oh, entropy is not really randomness. Technically, it's a bit more complicated than that, but for our purposes, it works to say that the more random stuff gets, the more mixed up it gets, the higher its entropy is, and the more likely that process, if it results in an increase in randomness, the more likely it is to be spontaneous or happen without a lot of help. So if you think about, your room at home, it doesn't spontaneously become more ordered. It doesn't spontaneously become clean and organized. Unless you have a continuous input of energy, it's going to over time become more random. As things kind of get cluttered and disorganized. So capital S is what we use for entropy, and so most spontaneous reactions result in an increase in entropy, which would mean a positive change in entropy. All right, so things tend to become more disordered or random over time. We just kind of said that. So what are some examples of, or some ways that entropy can increase? If we have a liquid that turns to a gas, so if you have a reaction where a liquid is becoming a gas, so for example, if I am talking about liquid water being decomposed and being turned into hydrogen, which is a gas, and oxygen, which is a gas, this represents, and we would have to balance it, right? We need 2 waters and then we need 2 hydrogens. But this represents a liquid turning into, actually in this case, 2 different gases, which means that there's an increase in entropy. Or I should say, at least a likely increase in entropy. There are other factors, other things that get factored in. Now, and I want to stop here and say, yes, entropy is probably increasing. We probably have a positive delta S in this reaction. But that alone doesn't mean that it's going to be a spontaneous reaction. Because if you remember, the first thing that we said about reactions being spontaneous is they tend to be exothermic. And this reaction is a decomposition reaction, so it's not going to be exothermic. To break water down, you're going to have to put in a continuous input of energy. So this is not necessarily going to be a spontaneous process, but it does have an increase in entropy. Okay, solid turning into a liquid or gas. And phase changes also work for this. So if you just have an ice cube melting, that's a solid turning into a liquid. So that would be an increase in randomness. If you think about it, those little water molecules are much more organized when they're in the crystalline state, when they're solid, than they are when they're liquid, and they can move around and flow. So the randomness goes way up when it becomes a liquid. And then if you were to let it evaporate, or if you were to boil it, it would go up even more because now you're becoming a gas. And then if you have a reaction where in the balanced equation you're producing more moles of stuff, of molecules or whatever you have, than you had in the beginning. So in other words, you start with 2 moles of reactants and you end up with 1 plus 3, which would be 4 moles of product. On the left I have 2 moles. On the right I have 4 moles. So that represents an increase in entropy, generally speaking. So it basically is like you're ungrouping or disorganizing. Think about at the end of class when everybody disperses and goes, through the hallway in their different directions. You go from being a class to being, 25 separate individuals. So you're ungrouping and you're becoming more random. Okay, so we can calculate delta S. And we can do this using the sheet that you already have, the little thermal properties table. We've used the back side of this sheet already for enthalpy. And if you notice here, we've been using the heats of formation from the left-hand column, but some of you guys may have noticed here there's another column, and it's entropy values. And they're smaller numbers, measured in kilojoules per moles times kelvins. And you can see another big difference is that even elements that don't have heats of formation, like aluminum here, do have entropy values. Because if entropy is just measuring randomness, then there's no reason that an element wouldn't have some degree of randomness. As long as the particles are moving, there's some randomness. And we're pretty much always at above 0 Kelvin, so the particles are always moving. Notice that gases tend to have pretty high entropies, where, for example, carbon dioxide has a pretty high entropy, whereas solids, like graphite, have pretty low entropies because they're much more organized, much more fixed in place, and so less random. Okay, so let's talk about using these numbers. It's basically the exact same thing as our enthalpy calculations. It's just the S of the products, and we do have to multiply by coefficients, and we do have to add up our 2 products and add up our 2 reactants if we have 2 reactants, and then just do products minus reactants just like we did with enthalpy. Okay, so go ahead and see if you can try, or go ahead and try this one on your own. Okay, and so there you see, there's the answer I got. I just looked up my entropy values first for nitrogen, so that was 0.192, and then 3, because the coefficient, times the entropy value for hydrogen, 0.131, minus my reactants, which I had just 1 reactant, but there were 2 moles of it, so 2 NH3, which is 0.110, and I get positive, delta S is positive here, 0.365 kilojoules per Kelvin. So that's an increase in entropy, an increase in randomness, which, we don't know about the physical states here, although nitrogen and hydrogen, actually all 3 of these are gases, but that's not given in the problem. But you could look at it and say, well, there's 2 moles on the left and 4 on the right, so we did expect an increase in entropy, so that this might be a consistent answer, and a good answer for that reason. Okay, so how do we determine once and for all if something is spontaneous? Because apparently a negative delta H is likely to make something spontaneous, and a positive delta S is likely to mean that a reaction is spontaneous, but it's not until we put them together with temperature and calculate something called free energy, or Gibbs free energy, giving credit to the person that came up with this, which is symbolized by capital G. It means the energy available to do work So basically, did the reaction leave some energy available to accomplish something, like gasoline burning and moving a car down the road? The work would be moving the car down the road. So here's your equation: delta G equals delta H minus temperature, and that must be in kelvins, times delta S. And if you get a negative value for delta G, then the reaction is definitely spontaneous. Okay, and so that becomes kind of like a once and for all, we know for sure. All right, so let's try a problem here using that equation. So find delta G for the combustion of methane. So first we need a balanced equation. So methane is CH4. If it's burning, we're adding it to oxygen, and we're getting CO2 plus H2O. And we need four H's on the right, so we need to put a 2 in front of H2O, and then we need to put a 2 in front of oxygen. So those are a balanced equation. And I should note here that because we do have two different entropies and enthalpies for water, depending on the physical state, when you burn something, you get water vapor. So the rest of these doesn't really matter because we only have one value on our table, but we do have two different values for water, whether it's a gas or liquid. So I'm gonna go ahead and indicate that it is a gas, because of course we don't get drops of water when we burn something. We get water vapor that we can't see. Okay, so we are given the temperature, and that's going to allow us to do the delta G calculation. So the equation we're going to ultimately use is delta G equals delta H minus temperature times delta S. And that's where the temperature is going to go in, is right there. But we don't know our delta H or our delta S yet, so let's figure those out. Let's first of all get delta H. Okay, so we'll go ahead and pause and do that right now. Okay, so I got negative 781.3, definitely an exothermic reaction. And obviously make sure that you multiply your coefficients, right? So this 2 here came from the 2 in the front of the water. Make sure that you use the water as a gas, so that's slightly different value there. And then, of course, there was nothing here for the oxygen because oxygen is just 0. So it should make sense that this is an exothermic reaction because it's combustion, right? So let's go ahead and find the delta S now. Oops. So delta S, the same way that we just did in our example. Okay, and so there you go. I got negative 0.004 kilojoules per Kelvin. So not a big negative value, but negative. So if I were to just look at the signs here, it would be hard to tell whether this reaction is spontaneous because both are negative. Normally we say, yes, delta H tends to be negative for a spontaneous reaction, but delta S tends to be positive. But if we can go ahead and use our delta G equation up here for this one with the temperature, 298 kelvins, we'll find out once and for all. So delta G equals delta H, which was negative 781.3 kilojoules, minus the temperature, which was 298 kelvins. And of course we want to make sure that that is in kelvins if it's given to you in degrees Celsius. So 298 kelvins times negative 0.004 kilojoules per Kelvin. And so on the calculator, I try this out, I get negative 781.3 minus the product of 298 and negative 0.004, and I get negative 780.108. So my delta G is negative. And really I'm going to stop at 3 sig figs. The only measurable number in this whole process that wasn't a book value or a table value is the 298 kelvins. So that has 3 sig figs. And so this is negative, which means that this is spontaneous. Which makes sense because combustion generally is spontaneous. Once I light that Bunsen burner with the methane in it, it's gonna keep going. It doesn't need continuous help.